So this is a video response to a user on the Scott Adams Dilbert Blog comment section. I was having a discussion with this user, and we were talking about climate, and the subject of the greenhouse effect came up. And the user just gave me their explanation for the greenhouse effect, and they were skeptical about the function of this greenhouse effect. And I believe that their sort of understanding of the greenhouse effect is based on a very common misconception. And this misconception is so common and pervasive that it kind of it hinders a lot of good discussions, because what happens is smart people like this user learn this sort of kind of good enough explanation for the greenhouse effect, maybe early on in school, college, something like that. And eventually they learn enough about atmospheric physics that they say, well, what I learned isn't right. I mean, that doesn't really make sense. So the people who taught me about the greenhouse effect don't know what they're talking about, and the greenhouse effect isn't a real thing. And so I want to clear up this misconception. And just to really quickly state what this misconception is. So there's this idea that the way the greenhouse effect works is, if we take this as a surface of the Earth and we take incoming sunlight, that sunlight gets absorbed by the surface, and it's in the shortwave bands, and that light gets re-emitted as long-wave infrared radiation from the surface. And there are these gases in the atmosphere who have the property that they absorb light in the infrared. So if they encounter this infrared radiation, it gets absorbed by the molecule and then gets re-radiated. So the idea is that half of it gets radiated up and half of it gets re-radiated back down, right? So half goes out to space and then half goes back to the surface. And that's how you warm the surface. You've trapped this heat in the atmosphere. And this is completely wrong. This is a misconception. I mean, there is this back radiation occurring, but you're not trapping this heat in the atmosphere. And in fact, that violates the laws of physics. I can't just infinitely trap heat in the atmosphere. If I was doing that, the Earth would just keep getting warmer and warmer and warmer ceaselessly. And that's not happening. All of this radiation that comes into Earth eventually has to make its way back out to space. Okay, so this idea that the greenhouse effect is supposed to act like a thermal blanket that's trapping this radiation in the atmosphere is wrong. That's incorrect. So if we know that that's wrong, the question is, well, how does the greenhouse effect actually work? And to understand how the greenhouse effect actually works, we need to quickly look at some really basic physics about how the Earth's temperature is determined. So at equilibrium, and that is to say that its temperature is neither increasing nor decreasing, it's at equilibrium, the radiation that Earth is receiving from the sun has to exactly be balanced by the radiation that it is emitting to space, right? And if we were to express that as an equation, it could simply be energy from the sun equals energy from Earth, right? And if we were to express the physical equation for the energy that's emitted by the Earth, we would do that using the Stefan-Boltzmann law. And it simply states that the intensity of radiation that's emitted from any object with mass is proportional to the fourth power of that object's temperature. So if we were to say that the energy that's coming out of the Earth, and that's like something like watts or joules per second, something like that, it would be proportional to the fourth power of the temperature times the Stefan-Boltzmann constant. Okay, so if we rearrange this equation, and this is also, I mean, you could break this up into a physics equation too, but it's not necessary. I'm just going to call this some number. I mean, the sunlight, incoming sunlight doesn't change unless something really bad happens in the sun, and it only changes by fractions of a percent generally. So we would plug this term in to our equation, and then we'll solve for Earth's temperature. Okay, so if we do that, we'll get something like the temperature of the Earth, so that's St, equals the fourth root of the sunlight stuff over the Stefan-Boltzmann constant. And this stuff isn't important. The important thing to know is that we have this equation that'll give us the temperature of the Earth at equilibrium just based on physics. I mean, there's no assumptions here. This is pure physics. It's just the physics of matter. And if we were to plug in the value that we know that the solar constant is, we can use satellites to measure how intense incoming sunlight is. So if we were to plug in that value and then solve for T, and of course we know the Stefan-Boltzmann constant, we would get a temperature that's about 200, sorry, that's not supposed to be a decimal point, 255K. And I don't know the exact conversion, but that's something around negative 18 degrees Celsius. Okay? So that would be the temperature of the Earth if it was in balance, if it was in balance with incoming sunlight, right? That's way colder. If I step outside, it is not minus 18 degrees Celsius, not over most of the surface of the Earth. It's much warmer. It's something like, I don't know, maybe 15 degrees Celsius, positive 15 degrees. So this is way too cold. So how are we in radiative balance, or how could we possibly be in radiative balance? I mean, the temperature of the planet is never this cold, right? At the surface, we're never this cold. So how does that happen? Well, the reason that happens is because we're not radiating energy to space from the surface, right? Where are we radiating energy from the space from? Well, if we go back to kind of this crappy drawing I made of the Earth's surface, right? And we have all these gases that absorb the outgoing radiation. Well, the radiation won't get to space until it's high up enough in the atmosphere that the atmosphere is so thin that that radiation isn't encountering any more molecules, or hardly any more molecules, right? Hopefully that makes sense, right? The atmosphere has to be optically thin enough that if I were to be looking upward in the infrared, my vision wouldn't be clouded, right? Okay? So that means that radiation is going to space from high up in the atmosphere at a high altitude. And that's really significant, because what do we know about temperature at high altitudes in Earth's atmosphere? So we'll say this is temperature, and A is for altitude, so this is the distance from the surface. We know that as you go up, as a general rule, the adiabatic lapse rate says that temperature decreases with altitude. So the higher up we get, the colder it gets. I mean, that's pretty intuitive, right? So we know that the higher up it gets, the colder it gets. And we'll say this is 280, something like that, our nice balmy surface temperature. And this is the layer of the atmosphere that's high and thin enough for radiation to escape from. So this is where we're radiating to space. Well, this is 280 and this is colder. And if we were to measure the temperature at this layer of the atmosphere, we would find that it was about 255 K. And that's the exact temperature that physics tells us the radiating temperature needs to be in order to match incoming sunlight. Okay, so this is the greenhouse effect. This is how these gases cause the atmosphere to be warmer, right? It's because of the adiabatic lapse rate. Because if this part of the atmosphere has to be 255 K to be radiating to space at that intensity, and we know it gets warmer down here, then the surface has to be warmer than the radiating layer. And hopefully that makes sense. And intuitively from this, we can see what happens when we add greenhouse gases, right? What happens? We add a bunch more gases to the atmosphere. We make the atmosphere more optically opaque. If I was to look upward from the surface, the atmosphere is cloudier in the infrared. So the radiating layer moves up higher. You have to go to a higher, thinner layer to get to space. And this higher, thinner layer is colder, right? So I've moved the radiating layer to a higher, colder layer. And now we are radiating energy at a rate that is less than the incoming sunlight from the sun. We're not in equilibrium. So now energy from the sun is going to come into the atmosphere faster than it's going out, and we're going to build up heat energy. And that heat energy is going to cause it's going to cause the radiating layer of the atmosphere to warm until it gets to 255 K and we're in equilibrium again. So now this higher part of the atmosphere has to warm. And because of the adiabatic lapse rate, the entire rest of the atmosphere has to warm as well. So this entire line is going to shift to the right. So adding greenhouse gases will move the radiating layer up higher. That higher, colder layer has to warm to match incoming sunlight, and the entire atmosphere has to warm as a result. And as a cool thought experiment, imagine if we had an atmosphere with a reversed lapse rate, right? So this is altitude, and this is temperature, and imagine that temperature increased with altitude. What would happen if we moved the radiating layer up higher? We added greenhouse gases in this scenario. We'd move it to a warmer layer, and now we're radiating faster than energy is coming in from the sun. Right, so we're losing energy faster than it's coming in, and this part of the atmosphere has to cool till it gets to be 255 K. So the entire rest of the atmosphere below it has to cool. So this line is going to shift this way, and we're going to it's going to shift this way. And we're going to cool the entire atmosphere. So in this scenario with the reversed adiabatic lapse rate, adding greenhouse gases would actually cool the atmosphere. So there's not some intrinsic sort of warming property that greenhouse gases have. It's the fact that they absorb this light in these bands and make it so it can't get out of the atmosphere until it's way high up in the atmosphere. That's what creates the greenhouse effect. So hopefully this cleared up that misconception. I'll post this on YouTube and then let you take a look at it and hear what your thoughts are. And hopefully this is useful.